Hi everyone, my name is Dr. Kevin Hainline. I'm an astronomy professor here at the University of Arizona. I'm really thankful that you've invited me to come speak to you all today. I'm going to talk to you about the earliest galaxies we know of, galaxies from the beginning of time, galaxies at cosmic dawn. These galaxies have been discovered in the last couple of years with NASA and the European Space Agency and the Canadian Space Agency's JWST, and they represent an incredible milestone in human understanding and thought. I'm going to talk to you today about how we discover these distant galaxies and what they've been telling us about structure and chemicals and the way that the universe has evolved from the Big Bang to today. So let's get going. It was 100 years ago when Edwin Hubble made the discovery that started us on the path of extragalactic science. At the Mount Wilson 100-inch telescope, he was observing this, the Great Spiral Nebula in Andromeda, when he discovered a Cepheid variable star that allowed him to determine that this object was millions of light years distant. When he discovered that, he realized this was itself an island universe, its own Milky Way. It wasn't within the Milky Way. And at that point, we started discovering more and more of these objects and finding their distances. And over the next 100 years, the farthest galaxy we know of at the time has changed dramatically. You can see it's gone through various epochs. In the 1960s, we discovered quasars, and our farthest object leapt in an enormous way. Finally, in the 1990s, with the advent of large telescopes like Keck and Subaru, we could confirm galaxies discovered by Hubble and find farther and farther galaxies, moving us into a realm where we're probing up against the Big Bang itself. This is our picture of what we've learned from discovering these galaxies. The universe was born 13.7 billion years ago in the Big Bang. The universe in its infancy was just light, and that light became hydrogen and helium and a little bit of lithium or beryllium, and then that hydrogen and helium sat for a long period of time, slowly pulled together in pools of dark matter. Those pools collected, and from them, the first stars were born. And those first stars were collected in large clumps that we think of as the first galaxies. And these stars were very energetic, releasing ionizing radiation that started to clear the ultraviolet fog of the early universe in a process called reionization. And so, over about 1.5 billion years, the universe changed state dramatically twice. Initially going from dark ages to the early structure and then reionizing to a neutral medium. We think at the same time that supermassive black holes were growing along with their galaxies, and so we can see all of this in a very small amount of time. The way that we understand this and the way that we see this is by looking at images like this one. This is the Hubble Ultra Deep Field in the southern hemisphere sky. This image was taken in the mid-2000s with the Hubble Space Telescope, and it is essentially a picture of galaxy evolution, where the farther a galaxy is in this image from our viewpoint, the longer it's taken for light to travel to us, and the farther back in time we're seeing the object. So for a spiral galaxy like this over here, we're seeing it, relatively recently. But for some of the farthest objects that we're seeing, that light may have traveled billions and billions of years to get to us. And the thing is because the universe is expanding, the farther an object is from us, the faster it's moving away from us, which means that we have what's called cosmological redshift. And the galaxies that are really far away, all of their light has been shifted to longer and longer wavelengths, so that they appear redder to our eyes. Even if the light wave leaves the galaxy as blue, as the universe is expanded, that light is stretched to the red, and so the farthest objects in here will appear very red. The problem with looking at an image like this is that maybe you would just select all the red objects, but how do you know if an object is red intrinsically because it's dusty or has older stars, or if it's a high redshift? How do you ascertain the distances to these very distant galaxies? The way that we do that across all of astronomy that starts with images like this is that we use a technique that was honed in the 1990s called the Lyman break technique. These galaxies contain, in and around them, neutral hydrogen. And neutral hydrogen acts like a filter for very, very energetic ultraviolet light. If that ultraviolet light hits a hydrogen atom, it'll knock the electron off, and that electron will go flying through the universe. And so that ultraviolet light will get absorbed. Light at longer wavelengths will pass right by the hydrogen, but at a specific set of wavelengths, 912 angstroms and shorter, the light will be absorbed by the hydrogen. Meaning if you were to take a set of images of a galaxy in a filter that probed wavelengths longward of that 912 angstroms, and then one that was at shortward of 912 angstroms, very ultraviolet light, you wouldn't see it in the ultraviolet image, but you would in the other images. And if you tune that to different filters based on the redshift, because remember, the entire wavelength of light from the galaxy is shifted to longer wavelengths as the galaxy is farther away, you can get a rough estimate of the distance of the galaxy. So for instance, let's imagine we took a picture of a set of galaxies in 3 different filters. This is Hubble Space Telescope's ACS, Advanced Camera for Surveys, taking a picture at 0.4 microns, 0.6 microns in the middle, and 0.8 microns on the right. These filters can be tuned essentially to find galaxies where that Lyman break, that absorption, is in the 0.4 micron filters. And if you look, there's a galaxy right here in the middle that I see, and then over here at the shortest wavelength, I don't see it. No matter how deep I look with Hubble, I'll never see it because all of the light at those short ultraviolet wavelengths are being absorbed by the neutral hydrogen in and around that galaxy. And when I use that, I can essentially say, 912 angstroms has been redshifted to between 0.4 and 0.6 microns, and I can use that to calculate the redshift of the object. In this case, we now know that the source is at a redshift of about 4. We can do a more careful job if we have a lot of data for the object, where we can fit using templates and models. Here, you're fitting the red data points, the observed data points, of which there's 6 detections, these are the red points over here, and the number of upper limits showing that the galaxy doesn't appear in all of those short wavelength images because of this Lyman break, this cliff that the model is showing dropping off right here at about 1.03 microns. Again, this model will be fit with redshift. You get a probability surface showing that the redshift of the object's about 8.5. You can do this across a lot of galaxies at once by taking images in different filters and looking for the objects that fall out, drop out of the shortest wavelength filters. When Hubble was launched, people didn't think that we'd find lots and lots of these distant galaxies, but over its lifetime, we've found incredibly distant galaxies. And as of 2015, the farthest galaxy that Hubble had found in these incredibly deep observations that it made was this object, GNZ11, discovered in Goods North, which is a field that's been well studied by many telescopes in the northern hemisphere sky. And this object was thought to be at about a redshift of 11. It was a record breaker. Really exciting. The problem is, it was discovered with HST's farthest longest wavelength filter, which was on its wide field camera 3, and that filter was at 1.6 microns, meaning if you wanted to discover galaxies at a higher redshift, the light would be shifted even farther into the infrared and Hubble wouldn't even be able to see it. So we had to wait for a telescope that was bigger, with better resolution, and operated in the infrared at wavelengths longer than what Hubble could see. Luckily, a telescope like that was launched in 2021. This is JWST. It has a 6.5 meter mirror, much larger than Hubble's mirror. It has 4 cameras that work in the infrared, and because it's an infrared telescope, it is cooled. You can see here it has this sun shield that keeps it entirely in the shade so that it can be very, very cold and operate in infrared wavelengths. The main camera, the one that has taken the pictures I'll be showing you in a little bit, is called NIRCam. It was developed here at the University of Arizona. I'm a member of the NIRCam science team. And the image that was the most exciting for me in the first, 6 or 7 months after the commissioning of the telescope was this one. This is the survey that I work on, the JWST Advanced Deep Extragalactic Survey, or JADES. And JADES is a survey that is a collaboration between the science teams behind the NIRCam instrument and the European NIRSpec instrument, combining 800 hours of what's called guaranteed time that you get when you build an instrument to make an unparalleled survey showing exquisite depth, filter choice, and area. And to show you the area, I'm actually only zooming in on this. Every object in this image, except the ones with the spikes over here, is a galaxy. There's probably many tens of thousands of galaxies in this one image alone, and I'm showing a zoom in. If I go here, you can see in the public data we have right now that there's an enormous region, and the Hubble Ultra Deep Field I showed at the top is just a small region right up here. This isn't even all of the data that's part of JADES. JADES encompasses some 224 square arc minutes of JWST near-cam observations across two fields, in GOODS South and in the Southern Hemisphere, and in GOODS North, where the Hubble Deep Field is, which is located right in the center over here. It's a combination of data here that is from JADES, along with data from other surveys that also observe this area of the sky using different filters and at different depths. And in fact, JADES is one of many surveys of the early universe that has been done by JWST. Here's a sampling of the footprints of some of those other surveys, taken from a review article by Brant Robertson. Right here you see that some surveys are incredibly wide, large area surveys that don't go particularly deep, which is why the color here is fairly light blue. It also doesn't have a large number of filters, just 4 filters, the Cosmos Web Survey. But it's designed to go after very rare objects where you need a large area to find them. Meanwhile, there are surveys like NG Deep down here that pool a lot of time into one small region, going incredibly deep to try and find the faintest sources. There's other surveys that kind of are a medium mix of those two. SEERS is an early release data set survey that was public almost immediately and caused quite a stir because of all of its exciting new science. And JADES kind of occupies a pretty cool space where, because it has GTO time, guaranteed time, it can be really deep with quite a bit of area and filter choice. One of the earliest things that we did was observe GNZ11 and take a spectrum of the object. Essentially, this spectrum acts as kind of passing the torch between the Hubble era and JWST's era, because while Hubble could only get one image of the object, JWST has spectroscopic observation capabilities in the near infrared, and we can get a beautiful spectrum of this object. You can see the cliff, the Lyman break over here on the left, such that you get no flux, no light to the left of that at shorter wavelengths. You see many little wiggles. All of these wiggles right here are emission lines from species of carbon, nitrogen, magnesium, oxygen. This galaxy is seen at a redshift of 10.6. And this spectrum caused an enormous stir among astronomers who raced to try and understand the different ionization strengths of these lines and their line ratios to understand what's going on in this object. Very compact. Some scientists think there might be a supermassive black hole growing in this. It's a very exciting spectrum. I went through our early JADES data and looked for all of the highest redshift objects that I can find photometrically using this Lyman break technique. And here are a sampling of these objects. You can see up here I'm showing images of the same object in different filters, and each row is a different object. And up here you see that the object is seen in all of the filters but not 115 or 090. And as you go down, they get to higher redshifts, such that down here, you're not seeing it in F150 at 1.5 microns. And so these are farther and farther, higher and higher redshift candidate galaxies. Brant Robertson wrote a paper subsequently with some of my objects to go even deeper with some other filters to really show how JADES is uniquely capable of finding some of these incredibly high redshift objects and differentiating them between actual high redshift galaxies and lower redshift objects that kind of look like they're really far away. Most of these galaxies are fairly compact. You can see they're like little nuggets of star formation, much smaller, significantly smaller, maybe 100 times smaller than the Milky Way galaxy. Here is the results of my paper showing every single dot here as a galaxy, and you can see that they stretch. You know, I went from redshift 8 onward. They stretch out to redshifts, candidate redshifts 14, 15, 16. We even have one at a redshift of 18, which is crazy. But these are candidates. We don't know if they're real or not until we go and get a spectrum of these sources. Excitingly, from my observations, I found that the galaxies in the early universe aren't just little smudges. They actually have structure. Here are a set of galaxies. All of these are real. Many of these have been spectroscopically confirmed. And they have multiple knots of star formation, sometimes connected, sometimes separated by a little bit. These knots of star formation demonstrate that these are probably massive galaxies in the making. Galaxies where we're watching them as they form into what will later become the large spiral galaxies and then eventually the large elliptical galaxies in our local universe. I like these galaxies up here because you're not seeing them, I'm not showing you them from far away. They are actually this close together. To give you an idea of how close they are, if you put the sun over here, the center of the Milky Way would be over here. This is about 7 to 8 kiloparsecs distant between these two galaxies at a redshift of 10.45 and 10.47. These galaxies are likely in some sort of kinematic pairing, where they are either coming together to coalesce or they, like to form some large galaxy. It's very exciting seeing so much structure. This was not thought to be the case in what we thought before JWST. To get spectroscopic confirmation of some of our galaxies, we took a sample of the highest redshift, brightest candidates in my sample and went after them with NIRSpec, another instrument on JWST. Emma Curtis Lake wrote this paper up with our results showing that the 4 highest redshift objects that we put onto slits with NIRSpec came back at the redshifts we predicted them. 2 of these objects had been discovered with HST, and then 2 were completely new, including JADES GSC 13.0, which is at a redshift of 13.2, which broke the record at the time, taking the record from GNZ 11. The first ultra-high redshift confirmation within the JWST era was this galaxy. This was a very exciting thing, but we weren't done there. A lot of different teams around the world searched for galaxies and found a number of them. And in our own data set, I found this object, which looked like it was at redshift 14, which is very exciting, but it gave me pause, because as you see up here in the top right, there's a really bright object, and then there's this blue thing. And they could be connected, they're touching, it looks like. But the thing is this object on the right, all of my code, all of the dropout selection that I was doing was telling me it was really, really far away. And this one, all my code was telling me was a much closer redshift of 3.54. We would go and get a spectrum of this object because we were so confused about what it could possibly be. And that spectrum confirmed it was in fact at the redshift we predicted it, a redshift of 14.2. This object is extremely bright. It is almost as bright as GNZ 11, but seen 100 million years before GNZ 11. It is a predecessor of sorts. You can see again the Lyman break, no flux to the left of that at shorter wavelengths, and this object is actually very different from GNZ 11 in that GNZ 11 is quite compact. Over here you see the radius and surface brightness. These orange points show that GNZ 11 is almost unresolved. It's very, very compact. But JADES GSC 14 here is actually relatively spread out. Massive weirdo. It is an incredibly exciting object, and it leads us to think, oh, there must be quite a bit of these types of objects. Here's an artist's rendition of what it might look like. I don't know if I like this very much because they've made it look very red, but in actuality, it looks red to us because of its being redshifted. It should be probably a lot more blue because of all of the young star formation in the object. Most excitingly, my former graduate student Jake Helton, who's now at Penn State, discovered that the object was actually brighter at longer wavelengths. At 7 microns, it was brighter than it was in all of the JWST NIRCam imaging. An instrument called MIRI on JWST was used to take this image, and it tells us something very special about JADES GSC 14. This galaxy has oxygen gas in it. It is a galaxy where oxygen is being excited by the light from the young stars and is fluorescing. But that means that oxygen exists in the galaxy in the first place. And the way that we get oxygen is that generation of stars has to have lived and died, expelling its oxygen gas into the universe such that it can be excited by the young stars. This has been seen in other objects in the early universe, where we're seeing oxygen gas is kind of ubiquitous in some of these early universe objects. That is telling us that the history of the universe is that stars came and went very, very early. Because remember, GSC 14 is only 290 million years after the Big Bang. So think about the stars that lived and died in those 290 million years so that we can have and see oxygen. This galaxy is at redshift 12, this one here is at redshift 10. So still, a couple 100 million years, and we have entirely clouds of oxygen gas that can be fluoresced by these young stars. Here's a picture of where we sit in terms of the magnitude, the absolute brightness of the objects versus the age of the universe. And you can see one exciting thing, which is that yes, JADES GSC 14 is not as bright intrinsically as GNZ 11, but it has a little bit of time to grow. And these dashed lines show how galaxies grow over time, such that, a kind of simple model for it, such that we might expect GSC 14 to even be brighter than GNZ 11. The problem is, we don't see a lot of the galaxies that are in this region where we expect some of these very bright objects to grow into, which leads us to wonder, why not? Even in large area surveys where we would expect to see some of these, we haven't seen a lot of these objects at these redshifts yet. And we're wondering what's going on. Maybe we're just seeing this object in some sort of state where it happens to be really bright when we're looking at it right now. Or maybe it doesn't grow in the simplistic way that we thought, and maybe it essentially stays around this brightness or even gets a little bit fainter over time. We don't actually know yet. That's why we need more objects like this to really understand it statistically. When we look at the evolution of the universe, like here JADES team member Lily Whitler has what are called luminosity functions, which essentially tell you how many galaxies do you see in a box of the universe as a function of how bright they are. So bright's on the left and dim's on the right. You can see that there's not a lot of bright galaxies, but there's actually more than would have been naively predicted based on early HST results. And if you go to even higher, higher redshift, farther galaxies, we're seeing that it's even more boosted compared to earlier observations. We see more bright objects and even more faint objects than might have been predicted early on in the history of JWST. That's really thrilling. To put it another way, this is this cosmic star formation rate density. How many stars are being born in a box of universe as a function of time across redshift. And so as you're seeing, as you go back farther in time, there's less and less star formation. But it kind of seems to maybe even flatten out based on some of this early work at the high redshift universe here, which is very different than what was initially thought to be the case. Early on, we thought that probably this may have dropped off a cliff, that we wouldn't see a lot of galaxies above redshift 14, 15, 16, but we're actually seeing quite a few. In the last couple months, we've actually discovered a farther galaxy. This is Rohan Naidu in the Mirage or Miracle program, finding a galaxy that beat the JADES record. This is a very exciting galaxy at a redshift of 14.44. It's very different than JADES GSC 14 in that it's significantly more compact. You can see its size down here, less than 100 parsecs versus many hundreds of parsecs for GSC 14. So we're seeing multiple styles of galaxy in the early universe, which is thrilling. And right here is our plot, kind of what I showed you a little earlier, but now I'm coloring these points by all the spectroscopically confirmed galaxies. This is not a full and complete list, but it's a pretty good one, showing you just how many early universe galaxies we have with JADES GSC 14. GNZ 11 used to sit alone, but now there's galaxies that Hubble could only barely see in some cases. And they're all stretching at different brightnesses and different redshifts with different sizes and morphologies and properties. It's a thrilling, thrilling time to be an extragalactic astronomer. We've come a long way in the last 100 years since we found the first high redshift galaxy, and we're moving up farther and farther. I think that while the record stands at 14.4, I think within the next year we're probably going to push to 15 or even 16 as we discover new and interesting faraway objects, and which hopefully are the objects that would grow into things like JADES GSC 14 or MOMZ 14 or even GNZ 11. And hopefully we also find some of the things that those galaxies become. I want to finish by focusing on this object right here, which was discovered in 1973. And it's an object that was a quasar, and Time magazine was very excited about its discovery and wrote an article about it. American Notes, The Edge of Night, 1973. I'm going to read a part of it here. The notion of infinity was conceived, as was the zero, by the Eastern mind. Yet it seems a peculiar Western need to determine the indeterminable. Scottish essayist Thomas Carlyle once noted that man must, quote, always worship something, always see the infinite shadowed forth in something finite. At the moment, the something worshipped is science, and the something finite is quasar OH471, the blaze marking the edge of the universe. But before the poetic notion of infinity is crushed between the calipers of science, it is best to remember that quasars were only discovered only a decade ago. More probably, what astronomers are really viewing is precisely what they've always viewed, the edge of their own vision. See, we are going to continue looking for these galaxies farther and farther and farther away, pushing back farther to the first actual galaxies we could possibly ever see as humans. It is a thrilling time to be an astronomer. The data that we're taking now will probably fuel PhD theses in decades. JWST will be around for 20 years. This is the tip of the iceberg. We are literally seeing the edge of our own vision. I cannot wait to see what types of galaxies in the next couple decades make this one, JADES GSC 14, or even MOMZ 14, seem quaint in the way that GNZ 11 now seems a little bit quaint back at the edge of Hubble's vision. Thank you so much. Have a great day.